of enthalpy. We are beginning with the concept of enthalpy. See, why we have to talk about concept of enthalpy? That is the first question. Because I told you in the earlier topic that heat is not a state function. Heat is not a state function because it is a path variable. Why is it a path variable? So I was telling you that heat is a path variable. Why is it a path variable? Because heat absorbed at constant pressure is not the same as, is not equal to, okay, heat absorbed at constant volume. So every time what happens when you are talking of energy change, because flow of energy is heat, no? What is heat? Heat is flow of energy. You are forced to, what do you call, every time tell what is at constant pressure or constant volume. Now we always in our study of thermodynamics would prefer to talk about state function where only initial and final values are required, because then it's easy to calculate and compute. Is this clear? So towards that, what happened was the scientists realized that most of the chemical and physical changes that we are coming across in our day-to-day life are constant pressure process. That means it's happening at atmospheric pressure, or even if you are what you call applying a pressure throughout the reaction, the pressure is same. Suppose you say A plus B forms C plus D, pressure of 2 atmospheres. So throughout the reaction, you are keeping the pressure at 2 atmospheres. It's a constant pressure process. So since this realization dawned on them that most of the what do you call energy changes, the heat change which is taking place is at constant pressure, they introduced a concept of enthalpy H. Enthalpy is given as what? H. Enthalpy is defined as the total heat content of the system. It is defined as total heat content of the system, total heat content of the system, including PV type of work, including PV type of work, okay, including PV type of work. So H, the enthalpy, is U, the heat content of the system, the internal energy, plus PV. But what happens is, what does this internal energy represent? That's where the problem will start. See, when we say internal energy, now is the time to talk about internal energy. See, internal energy is of two types. This is potential energy, and potential energy is made up of intramole and intermole, okay? And then we have kinetic energy. So kinetic energy is made up of rotational energy, vibrational energy, and translational energy. Kinetic energy is always because of movement of molecule. So within the molecule, what can happen? Now rotational energy, what happens? Listen carefully. Now if you talk of a real gas, this rotational energy, all this comes to be equal to phi by 2 Ft, okay, phi by 2 Ft. All these are basically a function of temperature, phi by 2 Ft. F is called as degree of freedom. And what is degree of freedom? Degree of freedom is that depending on the molecule, atomicity of the molecule. So there is a fixed value for a diatomic molecule, there is a fixed value for a triatomic molecule, and so on and so forth. So if this is also constant, internal energy becomes a function of temperature. Internal energy becomes a function of temperature. Is this clear? That's why in an isothermal process, what happened? Delta T became equal to, the change in internal energy became equal to 0. PV type of function. Now what happens over here is that H, you cannot find the absolute value of enthalpy. So that's the first thing. Absolute value of H cannot be determined. Why it cannot be determined? Because when we are talking of internal energy over here, we are talking about rotational energy, vibrational energy and all that, which represents microscopic property. I told you, the whole thermodynamics is concerned with macroscopic properties of matter and not microscopic. What are microscopic properties? Those which cannot be measured with instrument. So rotational energy, vibrational energy, translational energy, all these cannot be measured. So this involves a lot of microscopic properties. So absolute enthalpy cannot be calculated. If absolute enthalpy cannot be calculated, what can we calculate? We can always calculate delta H, the enthalpy change. So delta H will be equal to delta. So remember this from the entrance exam point of view, because absolute entropy can be calculated, but absolute enthalpy cannot be calculated. So everywhere we are going to say if it is an element at normal, normal temperature, enthalpy is considered to be zero, standard condition. Enthalpy is not normal, it's standard condition, is considered, remember the word, considered to be zero. So you are assuming it to be zero, it is not zero. And then we are building the story, it is clear. And why we are considering? Because absolute enthalpy cannot be determined. But what we can always determine is change in enthalpy H2 minus H1. So change in enthalpy is U2 minus U1 plus P2 V2 minus P1 V1. So delta H therefore is what? Now try to understand, since the whole concept of enthalpy is based on constant pressure. Whole concept of enthalpy is energy change taking place within constant pressure, in a constant pressure process. So that's what we are calling as enthalpy. Okay, heat content. Heat is what? Flow of energy. Heat content means the total flow of energy, but at constant pressure. So here what happens is P2 becomes equal to P1, and let's call it as P. So what happens is delta H is equal to delta U plus P delta V. So this is the enthalpy equation. Now how do we relate it to first law of thermodynamics? Let us look at it. How do we compare with first law of thermodynamics? Then we look at what is the enthalpy change in a solid, liquid, gas and in a chemical change. Okay. So according to first law, of thermodynamics, what happens? Delta U is equal to Q plus W. Delta U is equal to Q plus W. So when heat is supplied at constant pressure, first condition what we are saying, when heat is supplied at constant pressure, what happens? This heat is called as QP. So when you supply heat at constant pressure, the gas is going to expand. The gas in the cylinder is going to expand. When the gas expands, the cylinder will be pushed and mechanical work is done. What kind of mechanical work is done? It is a work of expansion. And therefore what happens? Work of expansion takes place, and that is minus W, minus P delta V, sorry. It will be minus W, that is minus P delta V. We have derived the equation. So work of expansion is negative. So substitute, what do you get? You get delta U is equal to Q minus W minus P delta V. So this Q becomes QP minus P delta V. So QP, the heat absorbed at constant pressure, becomes delta U plus P delta V. So comparing over here this equation, what do we get? So therefore delta H is nothing but heat absorbed at constant pressure. So remember, this statement is very important, okay? So delta H, enthalpy change, is nothing but, according to first law of thermodynamics, heat absorbed at constant pressure. So there we are defining the path. It is at constant pressure. Now what happens? Enthalpy change, enthalpy change for solid. See, in what do you call physics, effect of heat on solid is something you have studied. Suppose if I have a piece of copper, if I have a piece of copper metal, if I have a piece of copper metal and I supply heat to that Q, if I supply heat Q to that, is this point clear? What is going to happen? First of all, there is going to be a linear expansion. It's not that much. I'm just giving an example. So coefficient of linear expansion is alpha. Then the surface area is going to expand. That is beta. And because of total length, breadth, height increasing, there is going to be volume expansion. We know the connection, alpha is equal to 2 beta is equal to 3 gamma. Coefficient of cubical expansion. So coefficient of cubical expansion, gamma, for copper, I think it is about 10 raised to minus 7. So imagine if this was 100 centimeter cube copper, what is the increase in volume? Increase in volume will be 10 raised to minus 7. Whatever it is, 10 raised to minus 7 means what? 0.1, 2, 3, 4, 5, 6. So what is the new volume? 100 point. So hardly there is any increase in volume. So in a solid, we have the equation delta H is equal to delta U plus P delta V. But what is delta V, the change in volume? Very negligible. So P delta V will be very negligible. So that means in case of a solid, by this example, what do we come to? That delta H, whatever heat you supply at constant pressure, goes only in increasing the internal energy, that is delta U, and that is equal to mc theta, mass into specific heat into temperature change. This is heat capacity. So it's only going into increasing the heat capacity and not to do any mechanical work. Why? Because mechanical work is defined as P delta V. Delta V is a very, very small increase. So P delta V is very small or negligible. Is this point clear? Then the same logic holds for a liquid. So enthalpy change for liquid, enthalpy change for liquid will again be the same. That is, enthalpy change will be only internal energy change, and that is mc theta. Again, why? Because volume change is negligible. That definitely is more significant as compared to what you call solid, but in totality it is very insignificant. How it is insignificant, I'll tell you. Now, let us look at enthalpy change for a gas. Enthalpy change for gas. So if I have to explain this, I'll take an example to explain. See, suppose we have pressure cooker. Okay. How does the pressure cooker work? What happens is, in a pressure cooker, you have the container, you put only 250 ml, 1 glass of water, and then you seal it. There's a whistle. You know how it happens? We have taught you solution colligative property, increase in boiling point. What is happening is, 1 ml of liquid water, imagine 1 ml of liquid water is becoming 1800 ml of steam. 1 ml, that is 20 drops from your burette. It is clear, is 1 ml. 20 drops is considered to be 1 ml. 20 drops of water. But when it becomes steam, the volume of the steam is 1800 ml. It's 1799 times the volume of the liquid. So here what happens in case of gas, that's why in the cylinder we are putting gas. Because for a small energy change, the change in volume of gas is very high. That much change in volume creates a large pressure, and therefore it pushes the piston up to do mechanical work. It is clear? So enthalpy change for a gas, what happens? That delta H is equal to delta U, very little change in temperature, but maximum delta V being very large, 1800 times is the change in volume. Is this point clear? And then what happens? P delta V is a very large function. So in a gas, whatever energy we get by burning that fuel, a big chunk of it is used by gas to expand, and that causes pressure, and that pushes the piston. Why solid and liquid will not push? Because P delta V is very less. That's the concept. That's why I taught you in the beginning only engine. Why in an engine we put gas, air, along with the petrol. Oxygen helps in burning. It creates carbon dioxide and nitrous oxide. But these gases absorb the heat. There's a large change in volume, increase in pressure, and therefore the mechanical work is done. Now, the third is, so this third, now the fourth one is enthalpy change during chemical change. Now in an enthalpy change during chemical change, we can't use this because this is a physical change. Now expansion of gas, conversion of water into steam, and therefore the steam running the steam locomotive. It is clear, these are physical changes. So P delta V concept works. What will happen in case of what you call chemical change? See, in a chemical change what happens? P delta V is equal to PV2 minus PV1. I am not saying P1 V1 because the whole concept of enthalpy is constant pressure. So PV2 is N2 RT minus N1 RT. Why I am not saying N2 RT2? Because this concept P delta V we derived with isothermal condition. So temperature was also kept constant. So therefore this becomes what? Delta N RT. So in a chemical change what happens is, the equation for enthalpy becomes delta H is equal to delta U plus delta N RT. So what does delta N stand for over here? See, delta N means it is number of moles of product in the gaseous state minus number of moles of reactant again in the gaseous state. So if you look at the reactant and product, all those reactants and products in the gaseous state only are considered. Solid and liquid is not considered because they do not contribute to a large change in volume. So change in volume is because of volume of the product in the gaseous state minus the volume of the reactant in the gaseous state. This is the change in volume, and that change in volume is going to help in doing mechanical work. So this is very important. All reactants and products which are there in the gaseous state are only considered. So this is about enthalpy change, change. So this is a topic we are going to start, and next time also we'll continue. It is not as easy, it's a long process. Enthalpy change during physical change. So when we talk of enthalpy change during physical change, what are the changes we are talking about? First is phase transition. One minute. Phase transition. So when I say phase transition, that means what? We are talking about enthalpy of fusion. Phase is solid, liquid, gas. Okay. So we will have enthalpy of fusion, so delta fusion H, that is how it's going to be denoted. Then we have enthalpy of vaporization, that's going to be written as enthalpy vaporization H. And then we are going to have enthalpy of sublimation. Delta sublimation H. Then there will be enthalpy of what? Breaking of individual atoms and molecules, and then dissolution of substance in solvent and dilution of solution. These are 4. So let us concentrate today on this. There are 1, 2, 3, 4. Okay, enthalpy of breaking of molecules and all that. Let us concentrate on this. So how do we define enthalpy of fusion? How do we define enthalpy of fusion? So delta fusion H. Enthalpy of fusion is defined as the heat content change or the enthalpy change. Both words are correct. It is enthalpy change or heat content change. Enthalpy change or heat content change accompanying the complete fusion of one mole of a substance at constant pressure that is always there, because the moment you use the word enthalpy, constant pressure always comes in. Constant pressure and constant temperature. Boiling and melting, they take place at a constant temperature, remember that, and at constant temperature. People miss this word, and then in the definition they don't give marks. So let us now calculate enthalpy of I'll write like this, a symbol only. Enthalpy of fusion of ice when ice is melting at 0 degrees centigrade. It is clear. So we know that latent heat of vaporization, latent heat of fusion of ice is 80 calories per gram. See, we know that for ice, we know that latent heat of fusion see, in the textbook they have given directly plus 7.5 kilojoule, whatever it is, but in the exam they catch you that is the latent heat of fusion of ice is 80 calories per gram. Then what will be the enthalpy of fusion? You know the answer, but you will get shocked. What is it that they are asking? See, it's very simple. So you have, what is the 80 calories means what? You want per mole first of all. So 80 calories into 18. So that many calorie per mole ho jayega. Barabar? Then we know that 4.18 joule is equal to 1 calorie. So how much joule is this? So this is 80.80 into 18 into 4.18 joule per mole aa jayega because we multiplied by 18. So how much does this work into? Let us calculate. It is 80 into 18. Why we have put 18? Because 1 mole of water is 18 grams into 4.18. What is that? That is conversion factor. Is this clear? So that 88, I think. Just give me a minute. Something, I think I made a mistake in. Yeah, absolutely right. I'm right. I am right. I was looking at vaporization, sorry. So this becomes equal to how much? This is 6019.2 joule per mole. Or I can say it is plus. Why plus? Because fusion is endothermic. Heat is going to be absorbed. So this delta fusion H of ice to water at 0 degrees centigrade, that's very important, is plus 6.019 kilojoule per mole. We expect you to remember this value. Okay. Now in the same lines, we will use this space now. We are now talking about enthalpy of vaporization. So delta vaporization H. So what is enthalpy of vaporization? It is the enthalpy change. It is the enthalpy change, or we can say it is the heat content change enthalpy change or heat content change accompanying the vaporization, complete vaporization of what? Of 1 mole of a liquid. 1 mole of a liquid. Okay. Under what conditions? At constant pressure. and constant temperature. And constant temperature, correct? Because what happens over here is at constant pressure and constant temperature, that's the boiling point, 100 degrees centigrade. So here what do we get? We know that latent heat of vaporization of water. Now we are calculating for water. What will be the enthalpy of fusion, enthalpy of vaporization of water at 100 degrees centigrade? What will be the enthalpy of vaporization of water at 100 degrees, a constant temperature, that we have to define. So we know that latent heat of vaporization for water is 540 calories per gram. Correct? See, this is not directly values given in the textbook, but this is how we are calculating, and I need this for both NEET as well as JEE. If they give this value and then they will ask what is it at, what is in kilojoule per mole. So then there will be a problem. So what do we have therefore? Delta vaporization H is 540 into 18 into 4.18. So that will be kilojoule per mole. So how much does it work out to? Let us calculate. 540, okay, into 18 into 4.18. So this becomes, so this is 40.629 kilojoule per mole. I have already put the decimals. This is clear. 40.629 kilojoule per mole. Now what happens to the third part? What happens to the third part? Third part is enthalpy of sublimation. Enthalpy of sublimation. So delta sublimation H. Now how do we calculate enthalpy of sublimation of water? Now you will ask me, sir, does water sublime? Yes, water does sublime. This happens in a process called as freeze drying, or it is also called as lyophilization. Okay, I'll write the word. There is a process called as freeze drying, or it is also called as lyophilization. It's a very interesting thing, I'll tell you. You know what they do? I mean, when we talk of so much of wastage of vegetables in India, it is because we don't do food processing. This is one of the fruit processing that I am talking. Of course, it is used extensively in pharma industry also. What they do is, this is called as a lyophilizer. That machine is called as lyophilizer. Let us say we have got cauliflower. We just put cauliflower, cut cauliflower in the machine, and then we lower the temperature of the cauliflower to something like minus 30 degrees centigrade. Minus 30 now you are hearing very often. In the heights in Ladakh, it is minus 30 every day you are hearing. So using liquid nitrogen, there is a jacket in the machine. Using liquid nitrogen, what will you do? You will, bring the temperature to what? Minus 30 degrees centigrade. So at that temperature, what is going to happen? All the water in the cauliflower is going to freeze into ice, crystalline compound. Then what you do is, you apply very high vacuum. When you apply very high vacuum and then close it and then release the liquid nitrogen and put water at 30, warm water at 30. At 30 degrees centigrade, now what happens? The surface pressure is so less that water does not bother to become from ice to water to vapor. It simply sublimes. It simply sublimes. Advantage of this is that cauliflower retains its look. You understood? Then you can pack it. So this is how, rations are being given to army. Army gets, I don't know, in Bombay we have this Godrej ka nature basket. You will get freeze-dried pineapple, freeze-dried apple, and you are also getting freeze-dried pomegranates. The freeze-dried apple is like your crunchy chips. It's very crunchy. Of course, it's very costly. India is a very price-sensitive market. But you have to understand that if they put 100 kg of apple, I know because I had gone to an exhibition and talked to that fellow who was selling that. If you put 100 kg of apple, you get 20 kg of freeze-dried apple. It is like, crunchy. So what he was telling me, the biggest client that they have is army. So for the army they are supplying, they can just munch it. Na? So water sublimes. The whole story that I am trying to tell you is, water does sublime at a very, very low pressure. High vacuum, very low pressure is high vacuum, and 30 degrees centigrade. 25, not even 30. 25 to 30 they use. Is this clear? It's a very interesting thing. Suppose if at every district, if the government has one very large lyophilizer, the farmers can bring their produce, excess produce, you can lyophilize it, pack it, and it stays like that for about 1 year. You just have to open the packet, put it in hot water, your cauliflower, carrot, everything is what you call it. It's a very highly capital intensive machine. That's why government has to do it. Business sublimation. Now what happens? Listen carefully. So enthalpy of sublimation is delta sublimation H is equal to delta fusion H of water and delta vaporization H of water. Now vaporization H we calculated was at 100 degrees. So we have to subtract from that mc theta, mass into this thing. So what is the value? We have the value of enthalpy of fusion, vaporization of water at 0 degrees centigrade. So what will happen? Enthalpy of vaporization, this value. So at 0 degrees centigrade. So at 0 degrees centigrade, this value to we found out, delta sublimation H. This was plus how much? 6.01, and this is how much? This is 45.07. So this sum total becomes 51.08 kilojoule per mole. So these values you are expected to remember. Enthalpy of vaporization at 100 degrees was 40, and at 0 degrees this was 45.07 kilojoule. So this becomes the total value. Enthalpy of sublimation of ice to directly water vapor is 51.08 kilojoule per mole. These are all calculations which you require. Is this clear? For calculating all this lyophilizer and all, this is required. Have you understood? Is this clear? So this was the first part of enthalpy change during physical change. Enthalpy change, enthalpy of atomic or, so the second aspect of this is enthalpy of atomic or molecular changes. Atomic or molecular changes. There are three types in this. The first is enthalpy of ionization. Enthalpy of ionization. Then we have, next is electron gain enthalpy. Enthalpy of delta ionization H. or I. This is electron gain enthalpy. Delta electron gain enthalpy. Then the third one that we have is enthalpy of atomization. Enthalpy of atomization. And the fourth one that we have is, that's it, enthalpy of atomization. Then we'll have enthalpy of solution, that is a different aspect. So what is enthalpy of ionization? Enthalpy of ionization is defined as, it is the enthalpy change or heat content change when 1 mole of gaseous, from 1 mole of gaseous atom from 1 mole of gaseous atom 1 mole of electrons is removed. It has to be gaseous electron, gaseous atom, because otherwise they'll have solid, will have other force of attraction, heat has to be supplied for that also. In a gaseous atom only there is nuclear force of attraction. So whatever energy you are supplying is to overcome the nuclear force of attraction. 1 mole of electrons is removed, of course at constant temperature and pressure. So now when we look at the enthalpy values, ionization enthalpy values, hydrogen has a very high. So because that's one question that they have asked. They'll give hydrogen, lithium, sodium, potassium. It is clear. So remember, hydrogen has a very high ionization enthalpy. Hydrogen has high ionization enthalpy. Why? Because one electron is held very closely to 465 kilojoules. Electron gain enthalpy. So this was one question which we have to handle as far as entrance exam is concerned. This is clear. It has a very high ionization enthalpy. Then we have electron gain enthalpy. Electron gain enthalpy is what? It is enthalpy change. Now don't take it that it is always exothermic. Some teachers teach like that. 2 exceptions are there where it is endothermic. Okay, and that is a question which they ask in the entrance exam. It is the enthalpy change. It is enthalpy change when 1 mole of gaseous atom, 1 mole of gaseous atom accepts 1 mole of electron to form 1 mole of anion, 1 mole of anion in gaseous state. Everything. See, normally what happens, look at halogen. Halogen prefers to, what do you call, it has 7 electrons, it prefers to accept 1 electron and become 8. So for the ion to stabilize, it has to release some energy. It has to decrease its potential energy. So it releases some energy. I'll explain what I'm saying. You have chlorine atom. Chlorine has 7 electrons in the outermost shell. It wants to complete its octet. So it accepts 1 electron. So now it becomes chloride ion. Now if chloride ion wants to become stable, it has to decrease its potential energy. So how does it decrease its potential energy? By releasing energy. And this energy is called as electron affinity or electron gain. If it is one atom, it is electron affinity. If it is 1 mole of atom, then it's electron gain enthalpy. So normally it is exothermic. The exception, the rule. So now I'll write down. Normally it is exothermic. Exception to the rule. This is important from the entrance exam point of view. You have oxygen to O minus and O minus to O minus 2. What happens now? So this is minus 141. But moment it becomes O minus, adding the next electron, even though it is completing its octet, becomes very difficult. So you have to give energy to what you call, cause it to become O minus. Second one is plus 844. So the net reaction, if you see, O to O minus 2 is equal to how much? 3, then 0, then 8 minus 7, plus 703 kilojoule per mole. So the first mole of energy that it takes, it's always what do you call? It is always exothermic. But what happens is, if there is a second mole of electron to be introduced, it requires huge energy to be given to stabilize the anion. And so the net becomes endothermic. The other exception is sulfur to S minus and S minus to S minus 2. We know that stable sulfide ion exists. What is the value? 100 kilojoule per mole. And the second one is plus 532 kilojoule per mole. So the net reaction, if you see, sulfur to sulfur minus 2, it is how much? 3 plus 332 kilojoule. So which, now prepare yourself for the entrance exam question. What is it? That which reaction is endothermic? This is one thing that they ask.